Okay. I'm going to talk about what I'm obsessed with, is what I should say. And my obsession here is long building from working with the big ice sheet model, but also more recently working with a little bit with the kind of optimistic people who run global climate simulations and their belief in mass conservation, in particular conservation of all quantities that they simulate exactly in the discrete case. And so I have a need to communicate, and this is my attempt to think through enough to communicate an idea. But this is also going to be the simplest talk you've ever seen. That is to say, I'm going to talk about the simplest equation in any of these models, really. Probably the one everybody saw in graduate school and dismissed as uninteresting. And that's the mass conservation equation. I have a particular interest, though, because of the cryosphere connections, in fluid layers. Most of the modelable cryosphere comes not in big, thick things like the atmosphere, but relatively thin things like ice sheets or sea ice even, or subglacial hydrology. That's actually one of the things I'm thinking about. And for such systems, we have a thickness. It doesn't matter, by the way, if you're modeling the flux, which is there, shallowly or not. If you have a thickness and you think in terms of a sort of map plane view, your thickness changes according to two things, flow and climate. And I'm drawing climate in a sort of glaciologically standard way, which is positive is down. That is to say, the snow comes down. The point about the thickness here is that it's equivalent to mass. You want to conserve it, but also that it's non-negative. So some examples of this, I've actually have an organization here, a very deep organization. The top is Cryosphere, okay? And the bottom is not. But the other thing is that on the left, we have things that, by glaciers I mean not sliding very much. We have things that are highly diffusive, and there turns out to be models of the shallow ice approximation and what's called the diffusive shallow water equations are nearly identical. If you've seen one, you can solve the other. Your same code by changing a couple parameters. But then you have things that are really not diffusive, and ice shelves and sea ice are two of them. I'm not worrying really about sea ice or tsunamis. These over here, we sort of tend to think of that flux as coming from something that's not really diffusive. It's often distant pushing that moves our mass around. Okay, for an ice shelf, the mass moves because of inputs at the edge of the ice shelf. So what's the problem? And my answer is there is dirty laundry. And so let me go through some dirty laundry. Some of this dirty laundry has to do with our understanding of the physics. Some of it has to do with what we tell the users of models about what's happening. Okay? So let me start with the physics. The edge of the fluid layer is a complicated place. And of course, you may be thinking in terms of adding processes like calving or cliff damage and cliff falls on the edge of glaciers. But whatever your model was, it's a combination of the flux and the climate which determines the shape of the boundary. Okay? And it's a free boundary. That is to say, we want in prognostic models not just to determine how the object is flowing, but where the object is. In fact, and I think a lot of glaciological questions, the extent of the glacier is a really important question, maybe more important than how it flows. But the other kind of dirty laundry, the next two categories here, let me go back. Can I go back? Oh, okay, there we go. Is that, we talk in terms of ablation and accumulation, and we have to model it. It's one of the most important things to model in glacier context, maybe more important than modeling the flow. And off where there's no glacier, and I'm thinking in a 1 week time step. In a 1 week time step, you could have some warm days or some cold days. You could have the ability to melt away a lot of glacier over here because you've got some ablation. But during that time step, the glacier went away, and so you don't use that extra energy to melt glacier. Instead, it goes into warming up some rock, for instance. And you want to somehow communicate that to a user of a model. The other aspect is somewhere else, you might have a threshold. That is to say, there might be a mountain range which is currently unglaciated, And there's a threshold where if it changes, you've got to start up your flow model in the place where that was created. Okay? Now, a lot of people get away with modeling ice sheets and glaciers by assuming they have a fixed domain, and I'm not talking about that. I'm talking about models which are real prognostic models. So has anybody had this problem before? And the answer is yes. In fact, my real concern here is that codes become terrifying messes because of free boundary, ad hoc schemes for handling free boundaries. So I've actually selected my favorite three. I like all of these methods for very particular reasons. This is in PISM. This should be in PISM. This will be in some model after PISM. PISM is the ice sheet model event associated with most. And these are the best of the ad hoc schemes, but they correspond to code that is written with good physical intuition by smart people and maintained 20 years later by somebody else. Okay? So I don't mind if there's conditionals in my code. There are going to have to be conditionals in my code. But I can communicate to the future maintainer of the code, supposing that the code's actually worth keeping for a while, by saying what mathematical problem I'm solving, and not by a brain transfer 20 years into the future of what I was thinking about when I wrote those if-then statements. So that's my goal here, and I'm half done with my talk. I could really go, I'm done in the sense that the rest is sort of, okay, use the tools that are available, mathematical tools and computation tools. So I want to redefine the problem so that the free boundary is part of the solution, and use numerical schemes which automate the details, and then, I forgot to put it up here really, then be pessimistic about what's accomplishable. Is that a word? Accomplishable. Mm-hmm. Achievable. There's a word. And I'm making only one assumption about my numerical model. Okay? This relates to a practical aspect of modeling, is that you tend to produce time series. And these time series tend to be things like the total mass of the ice sheet every week. Okay? So my only assumption about the model that has this, in fact, probably has many copies of this conservation, one for ice, and one for land ice, one for sea ice, one for subglacial hydrology, one for supraglacial runoff. So I'm really thinking many copies of this, is that we've taken this conservation equation, we've discretized in time. Now this is a sort of mathy thing to do. What's over here is not a numerical method. It's another continuous problem for which we want to think about the free boundary problem. Using, for instance, big F, this big F of n might be the integrated effect of melt and precipitation over the 1 week time step, okay? And the Qn there is the unknown flux that you're solving for as you're solving for the unknown thickness. That's the Hn, okay? So this over here, in other words, is still a partial differential equation, and it still has this constraint that thicknesses need to be positive, and I'm assuming I have an old thickness and I'm computing a new thickness. Okay? The details of the flux are absolutely the issue. That is to say, the actual model code needs to care about what the flux is like. Is it an ice shelf? Is it an ice sheet? Is it a layer of shallow water in a tsunami model? But we all have this issue. And that's the most scariest slide I could come up with, I guess, but also the simplest idea I could transmit it with effectively. This will be the worst slide. From now on, it gets a lot better. The point is that we want to look at thicknesses which are non-negative. So this is what's called a convex set. It's all the things that are non-negative that are possible thickness functions. And we want to do something like a finite element method. Okay? Those of you who've done finite element method know that you multiply by a test function and integrate by parts, and I've done that. And when you think that through intuitively to get here, the next slide is more important than this one, you get a form where you've got a test function. Now the odd thing about this test function is that it's a difference, and the reason for that is that it's differences of reasonable thicknesses that are test functions, not just arbitrary functions which could be negative, which are not reasonable thicknesses. No, but this is the really important thing. So whatever you think about the previous slide, it's supposed to be describing a familiar equation for mass conservation. That's a PDE. Here it is again. Okay? But that previous slide didn't assume I know where the boundary was. I didn't know when I set up that problem on the previous slide, and I don't care about the details now. It didn't make the horrible assumption that most people building these models are making, is that they sort of know where to apply the boundary conditions. I didn't make that assumption. Instead, I said, I want this thing to be true everywhere in the domain. Okay? And that variational inequality on the previous slide actually implies two consequences. By the way, this is my only theorem, probably the only theorem in the section. It applies two consequences, one of which is where there's a material, you're solving mass conservation. And it also implies, and I think this is actually, I intend this to actually be interesting, it's the same statement which also says where you didn't have a layer, the climate was strong enough to remove it in the time step. Okay? We want both of those ideas in the same part of the code, okay? Because they need to be in the same part of the code when we're solving the same problem, because we actually want to predict where the boundary is in a sensible way. Okay? So this second part is saying, the old thickness plus an estimate of the integral of the climate over the time step was enough to kill it off. Okay? And I'm absolutely thinking of subglacial hydrology. I want to emphasize this again. I'm talking about all of the layers we have. So you've got lakes on the surface of the glacier. Those are fluid layers. You're probably not thinking of them as three-dimensional objects. You're probably thinking of them as a thickness. Okay? So this applies to each one of those species. I'm talking about one species at a time. The species which is glacier, the species which is sea ice, the species which is subglacial water. And they all have this property. And the climate, in something like subglacial hydrology, the climate is refreeze and melt. Okay? And you could have enough refreeze to empty the subglacial layer sometime during the time step, and it was enough, and all you know that it was enough, and you lost that. You can't, in particular, and this is what I'm getting to now, as I'm finishing up, actually, getting to what's sort of sad about this is that you cannot report exact discrete conservation for these free boundary models. So the only thing I want to show here is I've got a new state, which I'm computing, an old state, and I need to talk about the set, which I'm calling the retreat set. Okay? It's the set where I lost the layer and the set where the current layer is supported. In those terms, this will be perhaps as familiar as mathematics gets to geophysicists. If you difference, the integral of the thickness, here's a difference of thickness that's balanced by flow. That's the equation we're solving. But there's this extra part where you lost the layer entirely. Okay, so let me focusing now entirely on that extra. By the way, the climate, here's the climate, it's balancing the loss. But over here is this extra part. Let me call that the retreat loss. And what I'm saying is down here, that when you have a model running through an ice age cycle, you need to be saying, and I time stepped every year in that case, say, during each year, I had a climate which changed caused change in mass. But I also had some loss which I cannot balance exactly with the climate. All I know is that the climate was enough to kill off that part. By the way, I've broken a symmetry. You can talk about advances or retreats. Pick one. I'm a more negative guy, so I want to talk about retreats. And this is absolutely in the context of practical modeling. That is to say, we have a fluid here which is, along its boundary, effectively a fractal. Okay? I don't want a method which says, oh, follow the boundary and apply something along it if I can avoid it. Okay? So this inequality is actually exactly what we want. Currently, PISM does this, but explicitly and is therefore very slowly. Okay? That is to say, I'm describing something PISM actually does. Originally, I didn't think it was principled. Now I think it's actually principled. But I actually want it to be principled and fast as opposed to principled and slow. Okay? And also report better what it's doing. That's also this is a blow-up of the same picture. Once you're at 1 kilometer resolution for your model state, then you really can start seeing this fractal, and it really matters. But the other thing to say, and this is my entire description of numerics, is that there are new tools. And there are new tools that apply at this scale. And those tools allow you to solve this problem quite efficiently at big scale. Okay? And so the first thing I want to say is, even if your Q is proportional to h, it's a velocity times h, or it's proportional to the gradient of h. You know, you're solving the heat equation, you're solving the one-way wave equation. In either of those cases, the problem I'm talking about and the problem you are always solving if you're doing prognostic modeling is nonlinear. Once you have the constraint with thickness, that's the primary nonlinearity in glaciology. The primary nonlinearity in glaciology is that if it melts more than it snows, the thickness is not proportional to the difference. The thickness is 0. Okay? So that means that from the beginning you should probably just use nonlinear methods. Newton method is the only one anybody has. You can modify Newton method so it respects this constraint, and there are now tools, there are probably others than in PETSI, but that's a tool that scales. So, like I said, you could have fluxes which are hyperbolic fluxes, fluxes which are shallow ice fluxes. What I've said applies to all of those. This is my last slide. Those are two piles of stuff growing. To me, they look very similar. They have the same issues. They have a climate, they have a bed, they have a free margin. The point is that both of those can be solved by effectively the same numerical method, except for the one detail having to do with the flux, even though one of the fluxes is hyperbolic and one of the fluxes is diffusion. Okay? That's a hyperbolic problem of the type I'm talking about. Okay? So that's I'm done. I guess my points are entirely that this constraint should be part of the problem and that there are good tools and that you shouldn't be too optimistic when you're writing a proposal with a climate modeler and saying you're going to do exact discrete conservation, which I've recently done.